Welcome to Chapter 5, Probability. We're in Section 5.1. We're looking at the probability rules. Okay, so probability is, let's start at the top. It's a measure of the likelihood of a random phenomena or chance behavior. And probability describes the long-term proportion with which a certain outcome will occur in certain situations with short-term uncertainty. All right, so let's break that down with a probability experiment. So again, probability deals with experiments that yield random short-term results or outcomes, and it reveals long-term predictability. So our experiment, again, we'll go back to flipping a coin. So this is our experiment. And what are the outcomes in this case? What are those short-term uncertainties? Well, if we flip a coin, we could get heads or tails. And we don't know which one we're going to get when we flip our coin. We don't know if we're going to get heads or tails, but we can talk about the probability of getting heads and the probability of getting tails. It's half, right? Because there's only two. Okay, so the short-term uncertainty is we don't know what we'll get on the next flip. And then the long-term results, that's what we're talking about when we say like 50%. So 50% of the time we'll get tails, and then 50% of the time we'll get heads. Okay, so as far as this 50% goes, you know, if we maybe, I'll just do the little scratch work up at the top. If we flip a coin like 10 times, maybe we would get something like, you know, heads, 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 whoops. And then tails, heads, tails, tails, heads. What is that? 1, 2, 3, 4, 5. 1, 2, 3, heads and tails. All right, so we have 1, 2, 3, 4, 5, 6. So in this case, 60% of our flips were heads, right? And we just made this up. But if I do this for more flips, let's say I go out to 100 flips. All right, so this is, again, just some side work. You know, we would get 60%. But what do you think is going to happen with like 100 flips? Well, as we flip that coin more and more times, it's going to average out. It's going to start averaging out to be 50%. So as we get more flips, it will start approaching 50%. Okay, and then that's what we're talking about with the long-term results. And so how we interpret probability is we use something called the law of large numbers. So this says as the number of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of the outcome. So the proportion of the experiment, the proportion from the experiment gets closer to the actual theoretical probability. All right, so this is how we interpret probability. All right, so let's look at some definitions. So how we interpret probability. So the first one is we have an experiment. Probability, an experiment is any process that can be repeated in which the results are uncertain. Like flipping a coin, right? We can flip a coin over and over again, and we don't know if we're going to get heads or tails. The sample space of a probability experiment is the collection of all possible outcomes. An event is any collection of outcomes from a probability experiment. And when we're talking about the probability of event E, we write it as like a function notation, P of E. All right, so let's break those definitions down, again with our flipping the coin example. The experiment is flipping a coin. The sample space, we can use S, and again we can get heads or tails. And what can an event look like? Well, we could define our event. Maybe we're interested in getting just tails. So event E could just be tails. And then what would the probability of event E be? Well, it would be 0.5. All right, and then bonus round, it wasn't asked, but we are going to have to start interpreting these numbers. So we interpret probabilities using the law of large numbers up here at the top. So we could say if we were to repeat this experiment several times, maybe like 1,000, if we were to flip a coin one 1,000 times, we would expect about, again, 50%. And so 50% of 1,000 would be 500. So we would expect 500 of those flips to be tails. All right, good. Let's look at another example. Let's do the probability experiment of having 2 children. So identify the outcomes of the probability experiment. Well, let's see. We could have male or female children, so we'll just write M or F. So if you were to have 2 children, where's my F? There it is. You could have 2 males. You could have 2 females. You could have a male first and then a female, or you can have a female first and then a male. So the sample space in this case are just the collection of all those outcomes. So the only difference between A and B is we're putting part A as a collection, as a set, and that's our sample space. All right, and then we want to define event E to be have one boy. So event E, we need a bracket notation. Have one boy, that's these last 2 options. So there's 2 outcomes to have a boy. Okay, let's flip this over. We're going to look at the rules of probability next. And the first one is all of your probabilities have to land between 0 and 1. It corresponds to percentages, right? So 0% to 100%. All right, you can't be over-enthusiastic and say stuff like, I'm 105% sure. That doesn't work in probability. It goes from 0 to 100 and that's it. All right, the other rule of probability is that all of the outcomes, all the probabilities of the outcomes have to add up to 1. So let's write that out. So first, let's just suppose there's 4 outcomes, and we'll call them little e's. So let's say these are our outcomes. Then, if we add up the probability of all the outcomes, and again, we're going to have more than 4 outcomes in most of our examples, so we'll just extend this result to all outcomes. All right, all the parts add up to the whole, so they're all going to roll up or add up to 1. All right, let's take a look at our next example. And I typed out flipping a coin, but let's change that. It's actually rolling a die. A die has 6 sides. It's a square, and each side has an equal opportunity of occurring. Okay, so we're rolling a die, and again, it adds up to 6 sides. Okay, so what is the probability of rolling a 7 if you're rolling a single die? Well, is 7 even on there? No, so the probability of rolling a 7 is 0. All right, and then likewise, what's the probability of rolling a 1, 2, 3, 4, 5, or 6? Well, those are all the numbers on the die, so of course you're going to roll one of those numbers. Okay, so we have a special name for these things. When the probability is 0, it's called an impossible event. And when the probability is 1, it's called a certainty. Okay? All right, so let's continue on. We're going to go over a probability model next. So a probability model lists the possible outcomes of a probability experiment and each outcome's probability. All right, so it's kind of like a relative frequency histogram, but instead of the relative frequency, it's the outcome's probability. A probability model must satisfy rules 1 and 2 of the rules of probability. So let's look at this example. So we have that in a bag of M&M milk chocolate candies, the color of the candies can be brown, yellow, red, blue, orange, or green. Suppose that a candy is randomly selected from a bag. The table shows each color and the probability of drawing that color. We're going to verify that this is a probability model. So again, a probability model, it lists all the outcomes of a probability experiment. So we have all the colors here of our M&Ms. And then these are the outcomes, the outcomes probability. All right, so far so good. So the only thing we have to do now is to check rules 1 and 2 of the probability. So first things first, are all our probabilities between 0 and 1? Yes. All right, and the next rule. We want to know, I'll use summation notation, if all of the outcomes, all the probabilities of the outcomes add up to 1. All right, so little scratch work, 0.12 plus 0.15 plus 0.12. All right, does that add up to 1? Put it in your calculator, and it does. So we'll say yes. All right, so we can conclude, yes, this is a probability model. Okay, so we got some definitions out of the way. Let's go back to the interpretation of probability. And we already talked about how the interpretation of probability, again, is the law of large numbers, because probability itself, when we were first defining it on that first page of this packet, it describes, probability describes the long-term proportion of an outcome. All right, so again, it's the long-term proportion. So that's why we use the law of large numbers. Okay, so let's practice. So let's suppose event E has a 0.8 chance of occurring. All right, so when we go to interpret our probabilities, I always like to turn it into a proportion first. So going from a decimal to a proportion or a fraction, this is 8/10. So we can write it as 8/10. And again, the 0 matches however many decimal places. So we have one decimal spot in the 0.8, so we have 1 0 in the denominator. All right, and then to make this large, we can multiply top and bottom by 10. That's an allowed operation. So now this is 80 out of 100 experiments. We can multiply it by 100 originally. Now it would be 800 out of 1,000 experiments. All right, and now I'm going to use that because 1,000 is a big number. It's a large number. So this is saying the probability is 0.8. That's like 800 out of 1,000. So out of 1,000 experiments, we would expect about 800 times for event E to occur. So let's write that out. So the interpretation is we expect that event E will occur about, that's important because it's real life, out of 1,000 repetitions of the experiment. Okay. All right. More definitions, of course. This is the first section of a big chapter, so we have lots of definitions. Unusual events are going to be very important in inferential statistics. Unusual events have a low probability of occurring. It's going to be a huge theme later on. So we tend to say right now in this class, we'll say that an unusual event has less than 5% chance of occurring. So if we're calculating a probability and we find that the probability is less than 5% as a decimal, we would say that this is an unusual event. And unusual events are important because sometimes, well, an unusual event, it means that it has a low chance of occurring. So when they do actually occur, they can occur by chance. That's why people win the lottery. Even though it's a low chance of occurring, it still happens. But what normally happens, or what we assume, is that something else is going on. So maybe when we are setting up our experiment, we assume something to not be true. Maybe someone's cheating. Maybe we have data entry error. Who knows? Or something else is going on. All right, so that's why unusual events are important in this class, because something is wrong with the picture we're looking at, or else low occurring events wouldn't be happening. But we'll talk more about that in Chapter 8. Okay, so 3 reliable ways to determine probability. The first one is called the empirical method. Maybe you've heard of empirical studies before when they're looking at probabilities. Sorry, that's a C, E-M-P-I-R-I-C-A-L method. And this is what we've been calculating as relative frequency because it's from like an observational study or something. So empirical method, probability is really just a relative frequency. It's what we've been looking at up to this point. It relies on outcomes of a probability experiment all right, and again, I said it, but I'll write it again. The probabilities are really just the relative frequencies of an outcome or event. All right, the other way that we're going to determine probability, and the one we're really going to be focused on in this class because it's the most difficult to calculate, is the classical method. And the classical method is a counting technique. So we have to figure out how many outcomes there are going to be in total. And to use this, it requires equally likely outcomes, like heads or tails, or rolling 1 or 2 or 3 or 4 or 5 or 6. Those are all equally likely outcomes. Okay, so that means all the probabilities of each outcome is the same. Okay, and then how we calculate that, all right, we're going to introduce a new notation, NS. N stands for number. So NS is going to be the number of outcomes in the sample space. And then NE, N of E, is going to be number of outcomes in event E. Okay, and then the probability of E, how we're calculating probability with the classical method, we're going to count up the amount of outcomes in E and divide it by the number of outcomes in our sample space. Okay, and that's the one, this is the one we're going to be focusing on the most in this class. All right, and then finally the third one is the subjective method. And this is based on personal judgment because sometimes there's no other way to calculate the probability. For instance, when we're talking about maybe outcomes in sports, well, there's not repeated experiments we can do over and over again. We can't just have the same teams go out and play and then we look at the relative frequency of who's winning. So we can't use the empirical method. The classical method, whether or not a team wins or loses, those might not be equally likely outcomes, so we can't use the classical method. So sometimes we have to bring in sports experts and sports analysts, and they have to say their opinion about it. They have to say, well, I think did I name a sport? Let's just say Dodgers. The Dodgers have an 80% chance of winning, and I think that because of this, and this. So it's not like a wild guess. It's someone coming in and using their expertise to judge a situation. And it's still a reliable method of probability, even though it doesn't really have too much to calculate on our end. It's still very, very reliable. All right, so let's turn the page. In example 3, we're going to be finding all the different, we're going to determine what method of probability they used. So we want to know if they use the classical method, empirical, or subjective method. So this first one, and you guys can pause it and you can try it on your own and then you can compare answers. So the probability of having 8 girls in an 8-child family is this. All right, so notice they don't say, this isn't anyone's opinion. This would be a very random percentage to be an opinion. They don't mention anything about sampling or looking at, families with 8 children and counting up all the girls. So we have to assume that this is a classical method. Also, the probability of having a boy and a girl, that outcome is equally likely. It's 50-50 for the most part. So equal outcomes, it's a counting game, and they're using the classical method. Part B, on the basis of a survey of 1,000 families with 8 children, the probability of a family having 8 girls is 0.54%. So it's the same question, the probability of having 8 girls as before, but now they're telling us this is based on a survey. So this 0.54% is really a relative frequency. So this is an empirical method. All right, and then part B. According to a sports analyst, the probability that the Chicago Bears will win their next game is about 30%. All right, and that was the example I just used, except with Bears instead of Dodgers. So that's based on someone's opinion, that's subjective. And then finally, on the basis of clinical trials, the probability of the efficacy of a new drug is 75%. So again, because it's on the basis of clinical trials, this is like a relative frequency. So this is empirical. All right, let's look at our next example. Suppose a fun-sized bag of M&Ms contains 9 brown candies, 6 yellow, 7 red, 4 orange, 2 blues, and 2 greens. Suppose a candy is randomly selected. What is the probability it is yellow? All right, well, all of these candies, the actual candies, whether or not whatever color it is, but just reaching to the bag and picking out a single M&M, each M&M has an equally likely chance of getting picked because it's randomly selected. All right, so this is telling us we're going to use the classical method. It's a counting game. All right, so the probability that we're yellow, we have to look at the number of yellow, and that's given to us to be 6 yellow candies, over the total amount of M&Ms. And how many M&Ms are there? The amount in the sample space. So 9 plus 6 plus 7 plus 4 plus 2 is 30. So we have 30 in our sample space. So the probability that it's yellow is 6 over 30. You can say that's 1/5. You can call that 0.2. You can call that 20%. Those are all probabilities. All right, what is the probability that it's blue? So we'll call B for blue. How many blues are there? Out of how many M&Ms? Good. So there's our probability. And again, we're using the counting method or the classical method. So comment on the likelihood of the candy being yellow versus blue. Okay, well, which one is bigger? Yellow is bigger, okay? So we can say something like the likelihood of the candy being yellow versus blue. Well, the likelihood is bigger because the probability is bigger. So the M&M is more likely to be yellow. Because probability that it's yellow is higher than the probability of being blue. All right, let's continue on. So now we have an empirical study. We have that a survey of 500 randomly selected high school students determined that 288 played organized sports. So what is the probability that a randomly selected high school student plays organized sports? So first of all, because this is a survey and they determined that this many students played organized sports, this is telling us we're going to calculate the probabilities using the empirical method. So it's a relative frequency. All right, so the probability that they play organized sports, well, it will be 288 out of 500. All right, which was about, we'll say 0.576. All right, and now we're going to interpret the probability. Do you guys remember how to interpret probabilities? Good. Use the law of large numbers. So I like to turn my decimals into fractions. So 1, 2, 3 decimal places, that's 1, 2, 3 zeros. So we can do this. So we could say that we surveyed 1,000 students. You can even make it bigger by multiplying top and bottom by 10. So now you're sampling 10,000 high school students. And now that we have that, we can write our interpretation. So we could say that we would expect that out of 1,000 high school students, whoops, 10,000, about 5,760, again, about, would play sports. All right, so the law of large numbers. As our experiment increases, the proportion becomes the actual probability. Okie dokie. So final example, go ahead and pause it. You guys are going to do this one on your own. We're doing the classical method. It says excluding leap years from the following calculations and assume, here's this part, each birthday is equally likely. That's telling us that we're going to be counting things and using the classical method. All right, and then another thing before you guys go off and do this example on your own, because there's no leap years, there's 365 birthdays in a year. All right, so go ahead and pause it and then push play and check your answer. Ta-da! Okay, so let's go through these probabilities. The probability a randomly selected person, right, and that randomly selected part's important. That's what's making it equally likely. They have a birthday on the first of the month. Well, there's 12 months in the year, so that would be 12 birthdays out of 365. The probability a randomly selected person was born in December. December has 31 days, so it'll be 31 out of all of the birthdays. A randomly selected person has a birthday on July 5th. That's 1 day out of the year. And if you met someone and wanted to guess their birthday, are you likely to be correct? Well, that would be, if you were to guess, you would be right this percentage of the time, right? That's the probability of you guessing correctly, 1 out of 365. So no, that's a very low probability. And again, we call that an unusual event. That's our vocabulary word, unusual event if you do guess correctly.